Okay, so today we are hopefully going to get to the theorem of Ascoli-Arzela. I don't know. In some sense, everything we do today is building towards that, which will give us conditions that will that will force the existence of a uniformly convergent subsequence, right? So, just as we said before, in Rn, if you have a compact set and you have an infinite sequence in that compact set, then you're guaranteed a convergent subsequence. And our goal here is to, if you have a sequence of functions, what conditions do you have to impose upon those functions to guarantee that there exists a uniformly convergent subsequence of these functions, right? Because as we see, uniform convergence is the kind of convergence that we want for functions. Okay, so we start off with something that gives us pointwise convergence. But this is actually a key step in the proof of Ascoli-Arzela. Suppose you have a sequence of complex value functions on some set E. If E is countable and the Fn are pointwise bounded. So the values at each point are a bounded set. Then there exists a pointwise convergent subsequence. F and K. Okay, so let me start off with a simple question, which is, suppose that E is a single point. Okay. Then what's going to happen? You've got a sequence of functions on this single point, right? A sequence of complex values, on this single point, right? And they're bounded, right? So this is just Adam, you look like you want to say.
No.
Okay. So what is this? This is just just got a sequence. In that case you've got just an infinite number of complex points, right? And they're bounded. They live in some disk, and so by Bolzano wire stress, you know that there's going to be a convergent subsequence, right? Because then we're just dealing with a sequence of points, right? We're back in the sequence of points world again. Okay. Okay. So in that case, this is the same thing as Bolzano wire stress. Okay. So so then you're definitely guaranteed you get F and K such that F and K x1 converges. Okay, now suppose we have 2 points, x1 and x2. Okay, and you've got this set of functions, right? So these 2 points, I'm going to draw it like they're real, like E is the real line, and like the values are real, right? And for each one, you've got an upper bound, right? So all the values lie between here and here. All the values lie between here and here, right? And how are you going to get a sequence that converges pointwise on both of those points? Well, you can get one subsequence that converges on the first point, right? And then, what do you think? Anyone have an idea how to do it? So you have your first sequence, so can get an initial sequence f and k such that f and k converges on x1, right? But those values on x2, the values on x2 don't necessarily converge. But you've got an infinite, again, you've got an infinite bunch of points, right? If you look at the f and k, on x2, well, that's again an infinite collection of points, that is bounded, right? An infinite collection of numbers that is bounded, right? So you can choose a subsequence of these guys that converges, right? F and k sub L or something like that, right? Then choose f and k sub L, a subsequence that, then you can choose a subsequence that converges on x2, right? But it will also converge on x1 because this is a subsequence of, right, this sequence of functions is a subsequence of the sequence that converge on x1, right? So it converges on x1 and x2. Okay, so that's fine, and you can see what's going to happen if we have a finite number of points. We just do this n times, right? However many number of points, do that many times, and you get a sequence. Okay, but we don't have a finite set of points. We have an infinite set of points, right? We have a countable set of points, right? And so what we're going to do is, can anyone guess? We'll do I'll give you 2 points on the final if you make the right guess.
Triangle in a corner.
Not the triangle. Diagonalization. Fernando gets it. You don't need it. But you get it. We'll do a diagonal process. Yeah. Okay. So that's
Yeah. How can we guarantee the existence of such subsequence of L? So one extreme case might be that all the subsequences that converges on x1 is like f1, f3, f5, all the odd numbers, while the ones that converges on x2 is f2, f4, f6.
No. We only consider that subsequence that converge on x1. And we select from those guys. We throw out,
Yeah, then in this case, there does not exist any subsequence of.
No. You have to have one because of Bolzano-Weierstrass, right? Because so you've selected your first subsequence. It was f1, f3, f5, blah blah blah. This one works on x1, right? And then you look at the values. For consider f1, x2, f2, x2, f3, x2, blah, 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 right? Consider these guys evaluated at x2, and this is an infinite sequence in a compact set. So by Bolzano-Weierstrass, there exists a convergent subsequence of it. Okay. So you get a subsequence of this thing that will converge on x2, but it's still going to work on x1 because it's a subsequence of the original guy. Okay, so that's what we do. You say, okay, let E be xi from I equals 1 to infinity. since fn x1 n from 1 to infinity is bounded, there exists a convergent subsequence. Call it fnk x1. Okay, equals 1 to infinity. Okay. Now, it's mainly just a matter of notation. Notate f1 sub k as fnk. Okay. So this notation means the k is, of course, the kth member of the subsequence that converges on x1. Okay, so 1k. Okay, and then you iterate. Iterate. Since if you look at this function f1k at x2 is again from k equals 1 to infinity is bounded, there exists a subsequence f1 n sub k. Maybe if you don't mind, I'm going to use an n here. It doesn't matter. It's my dummy index. f1 nk x2, that's convergent. There exists a convergent subsequence f1 nk nkx2. Okay, so you're just taking a subsequence of the first subsequence, right? And you keep on going. Okay, so then again we notate f2k as as f1 nk. So it's the kth element, right? It's the kth element of the sequence that converges on x1 and n2, x1 and x2, right? So converges on x2 and the kth element. Okay, and so you keep on going, and you obtain a sequence, a grid of functions. Right, where this is the, these guys are the guys that converge on x1. These guys are the guys that converge on x2. These guys converge on x3, and so on and so forth. Okay. And as you see, each row is a subsequence of the earlier row. The nth row converges on xn and on everybody before. Right? And the kth element in the nth row occurs in the at least the kth place in the previous row. Because this is a subsequence of the previous guy. So everybody, this guy has to be, the first guy or beyond. This guy has to be the second guy or beyond. And then you can guess what we're going to do, right? We'll take the diagonal. Then this guy, this sequence of functions, is going to converge on each, converges on each x of k. So that's that's the idea. Is the idea clear? Is the idea clear? Right. So to make this more rigorous, you'd have to say, let's given some epsilon, let's show that we can make we can show that at x of k we have a Cauchy sequence, right? So we can make these guys within epsilon of each other, but that's easy to do. It's easy to do. So I'll just leave that to you as an exercise. So this is the idea. Right? You make this thing, and then you take the diagonal, and that's going to converge on everybody. So this is something that gives us a pointwise convergent subsequence. What we're hoping for is actually a uniformly convergent subsequence. We've got this this thing that doesn't really get us there, but it turns out to be pretty useful. Let me show you sort of how far away we are. So there's an example, or a question. Does, wait a second, sorry. Oh, no, it's okay, sorry. Suppose you have, say S of n is uniformly bounded. And pointwise convergent on the compact set. Does that imply that there exists a uniformly convergent subsequence? So, test exam question: true or false? Uniformly bounded and pointwise conversion on a compact set implies that there exists a uniformly convergent subsequence. The hint is it's false. It's false. And I think you have at least one good example. you remember we had an example of a non-uniformly convergent sequence of functions, which look like this: x to the n on 0, 1. Right? These guys, right? The first one looks like this, the second like this, the third like this, and so on and so forth. And they converge to the function that is 0 here, right? 0 here, and 1 up here, right? Right. But we saw that these guys weren't uniformly convergent, right? Because no matter, if you took an epsilon tube around here, there's always going to be some point where your function escapes it at the end, right? It's gonna jump out of the epsilon tube close when you get close to 1, right? Okay. So that's an example. These functions are uniformly bounded, right? They're all bounded by the number 1, right? They're pointwise convergent. They're on a compact set, but they don't have any uniformly convergent subsequence, right? Because if they did, they'd have some subsequence that could stay in the tube, but there's no subsequence that's going to stay in the tube. There's no infinite subsequence that's going to stay in the tube. Okay. So this isn't enough to guarantee the existence of a uniformly convergent subsequence. Okay. It turns out that the key condition is something called equicontinuity. Okay, so here it is. Okay, so you have f, a collection of a family of functions complex value. And if for each epsilon bigger than 0, there exists a delta such that if the distance between x and y is less than delta, then the distance between f of x and f of y is smaller than epsilon for all f in the family, then we say f is an excuse me, equicontinuous family on E. Equicontinuous family. Okay. What's the difference between, people are still writing. Hold on. Write faster. What's it? What's the difference between equicontinuity and uniform continuity?
For uniform continuity is like one in the past, like applying it, like all the rest of the function says that condition. But for this continuity is only one of them satisfied the whole thing.
Say it one more time.
It's like for this type of continuity, there's as long as you have one, like one element in the whole thing, like satisfy that condition, it will be.
No. I think you're misreading. If 2 points being closer than delta to each other makes the outputs less than epsilon for everybody in the family, then we call it an equicontinuous family. So you've got a bunch of functions, and this one delta, this one delta works for everybody in the family. Did you understand? Were you saying maybe I actually did understand it and I wasn't understanding you? No. Yeah, Jeff.
Is that like uniform continuity, but for every single function in the family?
That's right. That's right. So it's like everybody is uniformly continuous, and they're all uniformly continuous in the same way. It's a sort of I think of this as uniform continuity. Right? It's uniform continuity, but the delta works for everybody in the family. Right? Right? The delta works. This, you've got, somebody gives you an epsilon, and you can find a delta that if you take any 2 points in space, any 2 points in your space, and whatever function you want in the family, then the distance between the 2 points is going to be less than epsilon. Less than epsilon, right? So this is, if we just said this for a single function, that would be uniform continuity, right? That the distance, as long as 2 points are close together, then the outputs are close together, and it doesn't matter what points you choose, right? Continuity. So continuity is where the delta depends on the point, right? It depends on the epsilon, of course. It depends on the point, and secretly, although we didn't make it explicit, it depended on the function as well, right? So this was continuity at a point, right? And the uniform continuity was where it depended on the epsilon and, of course, the function, but not on the point, right? And equicontinuity is where it just depends on the epsilon and the whole family, I guess. Maybe I should say. Right. But it's sort of maybe better to think like this. Doesn't depend on the function, just depends on the epsilon. Okay. So let me ask the question: is every finite collection of uniformly continuous functions equicontinuous? Sure. Sure, because?
Because you can just find the minimum of the.
Because for each of the functions, there's going to be some delta that works, and there's only finitely many functions. So take the smallest one. That one will work for everybody. Right? Yes. Take delta to be the minimum of all the deltas for each of the functions. Okay. Okay. That leads us to following theorem. Suppose you have a bunch of continuous functions on a metric space. Okay. And you know that K is compact. And you know that these guys converge uniformly on K. then, in fact, the family is equicontinuous. Okay. Okay, so in my notes it says, make them do this. Easy. Okay, so I'll give you take a few minutes and see if you can get some idea, you think of something that might work. I think this is not so easy. Or maybe it's not so easy. But turn to somebody nearby and talk. See if you can say anything about it.
What was the last part? So every function is called like, yeah.
If y is less than something, all the rest of the so the indication and for all the functions, there's like a finite amount before that.
Yeah, we know that those have some.
Yeah, there's a minimum.
But then, what about beyond that?
Beyond that, so everything is in the band. You just choose the band. Like, you choose the band, the absolute smaller band.
Yeah, I think it's just.
You choose the absolute larger. You choose the band smaller than the absolute.
But they're
that maybe.
Wait, you can take this one.
Okay, so would somebody like to say something?
Yeah, I think that's true.
Winona, say something.
It's like, because it's converging uniformly,
Yeah.
after you pass on n, like
Yeah.
all the function will be in the band.
Yeah.
Like you just choose the band like smaller than that epsilon that you try to.
Okay, so let's take an epsilon band around around whatever it is that we're converging to.
And because it's continuous function on a compact set, it's the uniformly continuous by
Yeah.
itself, and there will be there will be a delta for like a delta works for all the function past that band, like past that point, like, and we know there will be finite amount of functions before that end.
Great, great. That's exact. So you're saying that, well, look, you choose this epsilon, you make, and past a certain n, everybody's going to lie in this tube, right? Everybody's going to lie in this tube, and you just pick one of the guys in there. That guy is continuous, right? But he's continuous on a compact set. He's continuous on a compact set, so he's uniformly continuous, right? And you can make everybody pretty close to that uniformly continuous guy, right? So, right. So those guys you can take care of basically, and then the guys outside of the band, there's only finitely many guys, right? And like we said before, well, these are uniformly convergent. I'm sorry. These are uniformly continuous functions. You've got a finite number of uniformly continuous functions, and so you can find a delta for those guys as well, right? So you get a delta for those guys. You get a delta for the guys that are in here, and then you use the smaller of those delta to control the whole thing. Okay. So I'm sorry to do this quickly, but here we go. Say okay. So fix epsilon. Right, since by uniform convergence, there exists an n such that n bigger than n implies, in particular, that fn x minus f capital N x is less than epsilon over 3 for all points. Okay. So we're using the Cauchy criterion, basically. But we're fixing one of them. So it's basically a Cauchy criterion.
Why are you subtracting f capital N?
So the Cauchy criterion is that there are n and m bigger than some number such that f of n minus f of m is less than epsilon over 3.
Mm-hmm.
I'm just going to choose that guy. I'm going to take that guy as my capital N.
Okay.
Okay. And so, right. So there's an n, and if these guys are past it, then they're past this thing here. So, yeah. So I'm just fixing one of them to use as a reference because I want to use his continuity or her continuity. Okay. So, okay. So now, by the previous remark, right? Since these guys are continuous on a compact set, they're all uniformly continuous. So we have a finite family of these guys, f1 through fn, is already equicontinuous. Right? You have a finite number of uniformly continuous functions, right? And that's the place where we use the compactness. So there exists delta such that if the distance between x and y is smaller than delta, then the distance between fi fix and fiy is smaller than epsilon over 3 for I equals 1 to n. So that delta, right, that delta works for everybody in the family, including f sub n. Including f sub n. And we want to see that that delta is going to work for everybody else, out, even past f sub n. Okay, so wait, but the thing is that everybody past f sub n is within epsilon over 3 of f sub n. Right. So if you're looking at anybody else, well, you take x and y, where the delta is close, where the distance here is smaller than delta. Well, then you see that the distance between f of x and f of y is going to be smaller than epsilon over 3 plus epsilon over 3 plus epsilon over 3. Right. Right. You just take the distance from here to here, the distance from here to here, right? This distance plus this distance plus this distance, and that's how you get it. So let me just write it out. For n bigger than n, if the distance between x and y is less than delta, then the distance between fnx and fny is smaller than, well, you throw in the f sub capital N guy, right? So f sub n x minus f sub capital N x plus f sub capital N x minus f sub capital N y plus f sub capital N y minus f sub little n y. Right? But this is smaller than epsilon over 3, and this is smaller than epsilon over 3 because they're in the tube. And this is smaller than epsilon over 3 because we're in the delta neighborhood. Tube. So you found a delta that works not just for these guys, but for everybody. Okay. Okay, that's it for today. Sorry to keep you over. Next time we will do, we'll start off with the theorem of Ascoli-Arzela.